Hello, and welcome to today's webinar on Is Your Data Architecture Ready for Microservices? I'm Christina Cardoza, News Editor of SC Times. Before we get started, I have a couple of quick housekeeping announcements. First, if at any time you have any questions about or during the presentation, you may submit them through the Control Panel's Questions tab. Secondly, this webinar will be recorded and available on demand through the sctimes.com website in about 24 hours after the event. Here at SC Times, we see organizations turning to microservices to be able to deliver software more rapidly, frequently, and reliably, but it's not always an easy transition, especially when you don't take your data architecture into consideration. Today's webinar will cover key aspects of data architectures and discuss what it means to separate state and business logic. Here to talk about this more is Dheeraj Ramella, a chief technologist at VaultDB. Dheeraj has over 23 years of experience in the field and has had the unique opportunity to work closely with customers, partners, and prospects when it comes to understanding their data management needs. Now to get things started, I will turn it over to you, Dheeraj.
Thank you, Christina, and thank you everyone for taking the time of your day to check out this webinar and see what I've got to say. So without further ado, I'm inclined to think that folks on this call are technical. And if you are in the same mindset as me, like when I go to a webinar, okay, enough marketing, let's get to the stuff. So no marketing here. We're just going to talk about microservices, data architecture patterns within that, potential pitfalls or gotchas, so to speak, and what does it mean in real-time applications? Because one of the things that I actually observed through my career is that every time you go to service-oriented architecture or any kind of loosely coupled architecture, there are ramifications of that on the data flow itself and how fast can you get your answers, right? So we'll touch upon all of those. This is a collation of my thoughts, and in the beginning it's going to be setting the frame of microservices, then a collation of my own thoughts, and looking forward to seeing what questions you guys have. I hope you enjoy this session. All right, so let's actually first start with the premise of what are actually microservices and why are they being talked about so much, right? So, and interestingly, this problem has been already attempted to be solved. I think everyone is familiar with service-oriented architecture, right? So it's very similar goals of it, if you think of it in those terms, but microservices takes it to the next step, which is the cloud nativity part of it, right? So it is essentially creating services with established interfaces, so independently they're maintainable, testable. Then you're actually having a loosely coupled enough framework that you can compose your application from these services. So when you're composing your applications, you can deploy the next version of a particular service independent of the rest of the application. That's a major benefit moving from monolithic architecture. So if you take a typical monolithic architecture application, you basically have some way of interacting with your user, what shows on the glass, so to speak, and then your business logic, what's behind the glass, and how do you interact with the actual data that represents what is being seen on the glass. That's the data access layer. So now take that and split it up into business systems and line of business capabilities lens. When you look at through that, like now you stop being just a pure technologist at heart, and instead you start looking at it to say like, okay, how can I actually decompose this application so I can recompose as I please? So that's the encapsulated business capabilities within each of these microservices. It could be a small one, it could be a big one, which is pretty much isolated or atomic level business capability, right? Now, coming from VaultDB, we can focus on the data patterns part of the microservices, not the entire plethora of the spectrum, right? So if you just look at the data patterns, like the most widely adopted ones are the shared data layer, Saga Pattern, and CQRS. So if you look at the shared data layer, it has advantages that, it is a single layer of truth for all the microservices within the application. So all the microservices are seeing the same version of the data. So a decision made in one microservice and an action taken in another would essentially tie well together because of the single version of truth, right? But the problem here is that when you look at the shared data layer, the traditional databases do not scale to modern requirements. I mean, of course, if you're a smaller shop or a smaller business unit that doesn't have scale problems, then it could potentially work. But if you're actually breaking down your application and you're looking at agility for deploying newer versions independently and fast, you're probably going to have scale challenges from your audience of your application, right? So in those cases, the traditional databases start keeling over, essentially. But the natural evolution of scale problem from data standpoint led to the NoSQL part of it. So NoSQL is great for the problems that it was designed to solve, which is essentially store data as fast as it arrives. One of the things that we observe working with our customers is that when the requirements of what you want to do with the data changes from just pure fast storage to incorporate smart processing on that data as it is getting stored to drive mission critical decisions, it starts becoming onerous because now you're actually adding multiple layers. We'll look into it a little bit later on as well. Most widely adopted, although, is the Saga pattern. Within the Saga pattern, you have two flavors of it. One is the event choreography, and the other is the command orchestration. Event choreography is like everybody talks to everyone else. They know how to talk to each other. On the other hand, command orchestration is I have a master orchestrator, so to speak, for a given business function, and it knows all the subsystems that which are the microservices, and how do they need to talk? What is the flow pattern of control flow within this business business unit to go through these microservices? In what sequence? In what order? What does the straight line path look like? What are the exceptions? All of this is master knowledge of the orchestrator, so to speak, right? But it becomes a single point of failure, the orchestrator, because now most of your business flow logic is actually concentrated in the orchestrator, and there are chances that this orchestrator could go down, hardware, software, whatever be the failure. How do you actually handle that? Right? We'll share some thoughts on that. Now, the third is interesting. It's almost like microservices lingo for a Lambda architecture, I guess. Like, just separate the read and write concerns, and you read from somewhere else, you write as fast as you can somewhere else. Perhaps you can actually batch load it into the reads so the reads catch up. On the other hand, you can probably have one system but your microservices could be the separation of concern layer, where your read works are separated out away from write, so you're not stepping on each other's toes kind of a thing. So these are the major patterns. I'm going to focus a little bit more on the Saga because I think the shared data layer and the CQRS have obvious gotchas there, because separation of concerns is going to lead to data consistency problems. Shared data layer, I'll touch upon it again later on because we have been used in a microservices environment as a shared data layer. So I'll actually touch upon the conditions under which that could work. But let's also talk about the Saga pattern, which is more prominent. Okay. So let's take the event choreography, right? So I place an order, and there are a bunch of things that need to happen. So first of all, does the guy who's placing the order have enough money to pay for this order? If not, then I'm not going to do any of the other work, right? So then if he does have enough money, then let me go actually take a look at the inventory. Do I have enough stock? If so, let me actually trigger a fulfillment so the warehouse robots actually pack stuff up and it's ready for delivery. And once the delivery is out, then I'll send an email notification to say, hey, confirmation email about your delivery is scheduled to arrive, blah, 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 right? So now, if you look at it, I don't know how many of you guys actually know the Toyota production system. Like, I am a process guy, like a process management BPM kind of a guy, like from my history. So one of the things that I studied was Toyota production system, and something that's really cool in that is the Kanban system. Kanban is essentially flagging, right? So I'm done with my work, I'm going to flip a flag, and then the next step, guy says like, the flag went up, so I'm going to stop my work. I'll stop picking things up from there and start my piece of the process work, right? So if you look at this flow, it's essentially that, right? So each layer is flipping a flag. The flag could indicate something like, in a production system, green means pick up the system. Orange means I'm still working. Red means like, actually, I have a failure here. I need a supervisor to come look at it. so be it, right? So that's production. Now here you would actually have what is represented in this diagram is essentially a straight line scenario. Everything is peachy, everybody is fantastic, boom, 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 you keep going on, right? So I call it like positive signaling and negative signaling. So positive signaling will keep you on the straight line, happy path, so to speak. On the other hand, negative signaling could be a variety at each single layer, right? So the payment service, was the payment successful? Yes, is one outcome. No, then what kind of no, right? Is it because he did not have enough credit on his card, balance or available credit on his card that he or she, that it got rejected? Or is it because the credit card number is invalid? Or is it because I was not able to get to the payment gateway service? There are several kinds of failures. So all of these failures need to be, shout out to say like, hey, this is why I failed to get the payment secure, and this is the reason. Now you'll have more services to process each of these negative signalings, right? And in this process, there's no rollback concept. Like, it's in nomenclature, you would see it as a business transaction rollback, but it's truly not a rollback. It's just you tell the other guy to say like, hey, can you undo the change that you just did? So you apply a compensatory mutation on the state to say like, yes, I actually took $20, but actually we don't have the stuff, so I'm going to just release the hold on that funds on your card. So if you look at the credit card funds system, like, a lot of the systems have the pending transaction flag, and that is to allow room for such backtracking, right? So, but if you look at all the exceptions that could happen at all the levels in a complex business process, your signal mesh can become a signal mess, essentially, right? Like, so how do you manage that? Like, if you are actually going to introduce new service into the process, then what are the signals that they need to be aware of? What are the signals that they should emit? All of this becomes a complex consideration. Okay. Now, we'll park this on one side. The other style of operation is the command orchestration, right? So here you basically say, all right, so instead of everyone knowing about everybody else, let me just have one master orchestrator, so to speak, that would actually know the entire business flow, and it is going to take care of how each individual microservice is going to be, invoked, so to speak, right? So here you're going to start looking at the inclusion of another layer, such as a message broker, because this provides a really well-designed loose coupling, but you're adding a layer, right? And the orchestrator now is becoming a single, I don't know if you guys are familiar with this or not, like, but in the earlier sessions, like, back in the day, you called them like nail sessions or pinned sessions. So you're essentially pinning an instance of the Saga orchestrator to do your job until the job is complete. Because otherwise you're going to have to like hand off control from one to another, and every interaction has to be a full round trip, meaning a neutral state to do the transaction and come back to a neutral state, and then you're done. So the orchestrator is free to do any other stateless work, right? But the problem here is that, like, if you actually don't manage all of the complexities of exception handling, you are going to actually end up with transaction orphaning. A lot of the terms here that you see, you can probably Google it because I just come up with these. So, the transaction orphaning is where, like, you went through half of your business transaction, but the failure signal was unhandled, and nobody's listening to that signal, and all of a sudden somebody dropped it through the cracks, right? So this becomes a design consideration. I wouldn't say an issue. It is, I think anyone that's worth the salt is going to do a thorough job. When you do a thorough job, this is a consideration you need to take into account, right? Now, the bigger problem is the orchestrator itself is becoming a single point of failure, if you think of it in those terms. Like, you can have a pool of orchestrators for every Saga, but if an instance that's participating in a business transaction goes down, what state was it in? What state was the business transaction, or all the business transactions that it has actually invoked? What are the states for those transactions? And how do I hand off this control to some other instance? Because now that this instance is gone, I'm going to pick another instance from the pool of the orchestrators and say, hey, you go pick back this work and then run it through completion. So all of this state management, just the orchestrator's flow control state management would require a separate store of its own, right? So your state machine for the orchestrator compared to a state machine for the business transactions. So these are considerations that you want to take into account, because if you don't, then again, you go back to transaction orphaning, right? So, all right. So one of the key tenets of microservice is, each service has its own database. It doesn't need to rely on a data store or state storage engine of another service, so they can all independently come and go, die and come back to birth, whatever the cycle be, right? So, but the problem with this is that in low latency action driving events, this is going to become a problem, because now the one that made the decision is looking at data differently than the one that's actually taking the action. Is that a problem in all use cases? Perhaps not, but low latency, mission critical, complex decisions, and you need immediate consistency on the data, because rollbacks are going to show differently in a compliance environment, right? So in those kind of cases, you want to be able to not federate between the related microservices, right? So that's one of the concerns. We touched upon this in the CQRS, right? So separating reads and writes into different stores essentially creates an artificial phase lag or a time lag of data transference from one layer to the other layer for it to be able to read the data that's just got written, right? So this is a consideration. How fast can you get this data from the write store to the read store? Maybe it is the same store and you just have API segregation, then that's one way of doing it. In that case, you're essentially falling back on the shared data layer kind of a model, so to speak. Now, when you look at each of the microservice, what we talked about Orchestrator, where am I in my process flow, that also comes into play at each of the microservice level, right? So because the microservice itself is doing a business transaction, but it could fail within its processing time scale or time frame, so to speak. So now you actually have a business entity storage for each microservice and its state machine for each microservice, right? So you can club them together, I guess, in telco. If you look at the 5G, I don't know how many of you guys are actually familiar with the 5G core. So moving from 4G to 5G, the component, what used to be called as evolved packet core, which controls the entire, how does your call get connected, who's billing at what rate, what policies should be applied, what security measures should be taken. All of that falls into what's called as evolved packet core. With the 5G network core, they basically said okay, let's actually convert this into a microservices architecture. So this has got close ties with our work in the telecom and carrier grade application world as well. So when you look at the data there, they essentially say okay, let's centralize the data, but separate it into the user, i.e. you and I, right, subscribers, our data, subscriber-related data, and our policies and rules and applicability into one data store, and then the state machine data of the actual individual components and services within this network core into a separate one, UDR and UDSF. But different topic. So just basically want to be conscious that whatever you're thinking of, you actually have an entity-related data and state management-related data. So this needs to be either at each service level, or you can consolidate it as a common shared data, but bifurcated shared data across all services. Now, this is something that this is not data problem, or this is not technology problem. This is more like a organization, people, and putting your thoughts around how to go about moving a monolithic application into a microservices architecture, right? So this is a process problem. A lot of the times people say oh, I'm just going to take this small piece and actually I'll just build a microservice around it. Now everyone else can actually use it. But I understand the phased approach part of it, but then if you actually do not have an organization-wide cohesive approach and plan to say okay, in what phases, what capabilities would move to the microservices world, you're actually going to end up with what you have today, which is shadow IT, right? So in any large organization, if you look at it, like, each line of business has this skunkworks IT. They have their own Excel spreadsheets or Access database where they actually take dumps from the main operational database and dump it into their Access, and before you know, like, no one is seeing the same data anymore, right? So that's something that you must take into account, that it has to be an organized, methodical, systematic approach to say what business capabilities would need to move to this new universe, and have a copy, have only one copy of each, right? So otherwise you're going to have each microservice business capability being replicated across lines of business, and before you know, you have like various versions of how to do business. Okay. Now, I've been using the bifurcated nature of state and logic, right? Like, so one of the things that our customers come to realize working with us is that, when you break down an application, because one of the key concerns for microservices is separation of logic and state, very naturally so, right? Because you want to have a stateless container that can come in and go out and nothing is lost and state is managed somewhere else. But when you look at the business logic itself, there are two types. It's a nuanced differentiation there. One is the application flow control logic, like, okay, so this field is entered, so I have to disable the button. This is the current application state, how the screen is being shown, all of that is your application flow control logic. That's truly stateless because it's just the state is within the session. The session goes off, the state becomes unnecessary at that point, right? But on the other hand, the more interesting part of it is the data-driven decision-making logic, right? So when an event happens, an action needs to be taken. The action could be don't do anything either, right? So, but to get to that point, you need to have the processing and notification in between done as fast as you can. So this, in my linguistics, I call it data-driven decision-making logic, right? So that's one. Then on the data side, we just talked about it, right? Like, so the two stores. One is the application state machine data, and the other is the business entity related data. What we've actually come to understand is that the maximum value is being elicited by our customers because they're actually able to house both the data-driven decision-making logic and the data within VoltDB, so they're actually able to scale congruently as to how much data is there, how much processing needs to be done, and at scale, linear scale, right? So this reunification of separated twins, so to speak, the data and its related business logic, is something that's really important, but that doesn't get actually touched upon in many places. When you research upon microservices, you wouldn't see this. It stops at the first level of you need to separate business logic with data. So it's a second level consideration that one must actually take into account to say, okay, how much of my work needs to be done in low latency manner? And how much work do I need to do those jobs? And if it is really a lot, moving data back and forth from a store to a processing layer becomes really, really problematic, right? And that's where one of the pet peeves that I have is, like, I hear a lot of NoSQL, technology proponents basically saying, hey, NoSQL is the best because you can actually just store anything you want and get anytime you want, and no worries at all. Like, but the problem is you are actually moving the payload, whatever be that payload, right? So you want to do some work on that entity's information. You're taking a large chunk of the object. I've seen this in telco world time and again, right? So they come in saying like, I need to move 25 kilobytes of payload from store to processing layer, and I'm not able to go beyond 70,000 transactions per second. I also have a 40 Gbps switch. How come? Like, that's because you're moving 25 kilobytes, right? So that's a lot of data to be moved back and forth. Network bandwidth is a very, very precious commodity when it comes to planning your physical infrastructure and topology. And you don't want to be frivolous with that, right? Like, so another thing is, like, okay, NoSQL has several flavors. NoSQL is, no SQL, and then it became not only SQL, and then now it's like actually no SQL, right? So because they're actually all implementing a SQL-like skin on top of their internal storage anyway, because they see that the maturation that the SQL language has gone through is not transferable in very, very easy terms into a concocted up language, right? So every NoSQL technology out there has its own way of interacting, and this is actually kind of funny to watch it from the sidelines, because you look at like everyone solving the same exact problem their own way, but actually achieving the same thing, which has already been achieved. So wait, what? So it's kind of funny, like when you sit on the sidelines. But if you are in that quagmire, it's purgatory, right? So you want to get out of that. So the one of the things that I actually have here is this is like an AWS, I think C4 large, or one of those models, and this is the inter-container speed. If you look at it, 740 Mbps. It's not even 1 Gbps, right? So of course you can get more bandwidth if you pay more. That also means that what kind of instances you're taking. You have to take the highest end instances to get the 10 Gbps and 25 Gbps. Now you actually throw containers over that. It's actually going to separate out your available bandwidth into and divvy it up across these containers, right? So then when you look at all the development that has been happening in the networking world, the regular networking to SRILV in the virtualization world, and then DPDK, all of these are technologies that are actually trying to eke out just a little bit more network bandwidth efficiency. And then you throw NoSQL at it. It's like you work really, really, really hard to create this masterpiece, and you just put it in the basement. No one actually is seeing it, right? So it's the same way. You do so much research to eke out more performance in your bandwidth optimization, and you turn around and actually do mindless job of moving data. I think it's frivolous, right? So we can talk about it, I guess, offline. I'll try to be very polite about it. So, right. Now, the space that we talk about, because VoltDB is all about fast data and real-time interactions and decisions, will contain within that space just from the relevancy standpoint, right? So there are several applications that you can actually break down into microservices and not worry about any of these latency considerations or complexity or complications. Very super tolerant services where you can even lose data and nobody cares because it's just sensor data. If I did not actually act on it right away, it's already gone anyway, right? So that's okay. But again, within sensor data, you have examples where it's really, really important to know what my data is telling me instantaneously within milliseconds, so I can actually avoid any hazardous or catastrophic event that could stem if that were to progress as a trend, right? So in this kind of real-time environment, we broadly look at data as two ways of data utilization or value elicitation. One is stream processing, where there are multiple actors that need to tap into that data's value at their right area, and they create actions, notifications, alerts, whatever be it, and then kick the wall down to another layer, another layer, another layer. So by the time you're through the fifth or sixth layer, you're essentially done tapping into the fast data real-timiness of the data, right? There's a whole slew of other applications that are dependent on responsive interaction. Think of typical database type interaction, right? So here is an event. I have a question. What is the answer? Take this event into account and give me the answer. If you don't, then I'm going to be wrong in the action I'm going to be taking. So these are mission critical applications. Think of credit card fraud prevention, right? So should I connect this call or not? I don't know if you guys actually follow this or not. It's funny that Wangetti finally made it to the United States. So Wangetti is one ring fraud on telecom. So this is very prevalent everywhere else. So I was very surprised that it took so long for it to show up here, but it is here now. So the way the fraud works is that there is a ring that comes through and you missed a call. One ring, you missed a call. And you look at the number and say I don't know this number. I wonder what they want. And you call them. and it's actually a long distance call. So now they tap into an international or high price, like, you know, the 1-900 numbers kind of rating system, and they are actually charging you, the caller, for their profits, right? So one of our partners working in the European area, their you know, transactions are mission critical because they need to know if this ring should even happen, right? Is it a blacklisted number? Is this number that has been actually doing this several calls that are only one ring, and that's actually you know, in quick succession, because it's robotic. Like, I don't think people actually dial numbers, 10 digits, 24 digits, and things like that, and wait for one ring and drop it. That's not an efficient way of committing fraud. If you want to commit fraud, do it really fast, right? Like, so they do robotic. So all of these rules are learned from the machine learning elements of it, and then they bring it in, and they say, like, I can actually make a decision like that within less than 5 milliseconds, if I should even connect this 180 call, right? So you're preventing fraud, not reconciliating and saying, like, okay, what is the damage done? Let me see how much I can recoup out of this, and I'll write off the rest of it. Because when it was small, it was acceptable. Now when it's being robotic, it goes into millions very, very quickly, right? So those are the mission critical. That's one example. The another one is credit card fraud prevention, right? So you swipe a card, and is it a stolen card? Is it, when was it last accessed? Is it a no card show transaction? All of these rules need to be applied before I create an authorization code for that swipe. So before I even actually charge the card and then wait, you'll be able to say, like, this is fraudulent, I'm going to prevent it. But how do you do that? Like by incorporating machine learning insights. But one of the big things in fraud is what's called false positives, right? So it's like, it's a fraud, like, but it's actually genuinely the right thing to do, because I called my wife because she was traveling in Europe, and then I gave her my credit card number, and she placed a trade, right? So then you can actually incorporate a two-factor authentication and things like that. So there are a lot of ways to do this. But all of these require ever improving, better decision-making, complex decision-making in sub-millisecond or sub-single-digit millisecond level. These are interactive. These are responsive, right? So now, when you look at a stream, I don't know, if you guys know what event time and process time is. So event time is when the event happened. Process time is when my system saw the event data come in. So typical way of stream processing is event time windowing or process time windowing. So both, like, we think that's an artificial calibration of when I should do some useful work with what I have accrued as data. Because within Volt, like, the way we operate is that, like, when the data comes in, you keep storing, keep looking for signals. As they are getting completed, you complete the business event, and when the business event is completed, you take the relevant data and push it over to an archival store or a ledgering store. So we look at it as continuous processing versus time window slicing. So it's just the way that we look at it, right? So when you look at what needs to happen to extract value from real-time data, you can read these, state management, enrichment of data, making a decision, aggregation for KPI monitoring, and applying what I learned from my training data into new set of rules or ever-enriching rules. Okay. So what does all this mean? Are we a database? Should we do this with database? NoSQL store? Should we do this with streaming technology? Actually, it's a combination of everything, right? So you need a multimodal database that also has stream processing capabilities built in together. I'm not saying this because Volt requires it, but I'm just saying this because our customers are able to peel away from their competition by using Volt in such a manner, right? So it's the convergence of state and stream processing together to say, like, okay, I am going to process the incoming stream as it is arriving while managing the state within a single store, single layer, because my latency is my king. The fastest I get to the most correct action, I'm that much better than my competition, right? So you have to think beyond the Kappa architecture where, like, I'm already streaming, distributed logs. Can I just use these logs for reprocessing some other data? That's nice that it serves a certain set of use cases. But if you think of mission critical, low latency, high complexity, need immediate consistency, when all of these come together, you want a layer that brings together the state and stream. Okay. So what we vie for as an organization is do everything real time, right? So don't think in terms of database, don't think in terms of streaming engine, just create, even if it means it's a brand new platform of thinking or framework of thinking, convergence, state stream, or, streaming state, whatever you want, right? Stateful streaming, whatever you want to call it, it's a new category and new caliber of workloads that are becoming mainstream slowly, right? So, the key requirement is single-digit millisecond latency and your event to action cycle, event decision notification action, right? So this is how I look at a data flow. The event happens, comes in, you need to make a decision, you send a notification to an actor, the actor acts, and that action creates an event, another decision needs to be made, and so on and so forth, right? So when you have multi-layer, this was one of my peeves with even service-oriented architecture, right? So loosely coupled means it's easily, removable, dismantleable, recomposable. That's awesome. That's fantastic. But in strict latency manner, so every loosely coupled layer is adding immutable latency to your process. So that means that you cannot do away with that latency. That is your baseline latency. Anything that you want to do above and beyond is only going to add more to that, right? So what does that do to your business SLA? Telecom is going towards single digit, like 1 millisecond, right? So is that going to support it? Perhaps not. Most likely not, right? So not just that. Now, every time you add a layer, when that layer, an instance of that layer fails, how do you do an elegant handover from the dead instance to the next instance? Right? So how do you restore the transaction state and progress from where you stopped to see the transaction to completion? These are all considerations you need to take in the overall architecture itself. Okay. So again, the last one is about don't move data because you're actually taking time to serialize and deserialize data. Send it over the wire, deserialize on the other end, and you're actually having to peruse through the entire object's contents to figure out what you want to interact with, change it, serialize it, send it over, and then deserialize it on the other side, right? So this is very, very expensive process. Like instead, actually think of, hey, I want you to do this job, and here are the parameters that you need to take into consideration when you're doing the job, right? So parameterized job invocation. That's how I think of the world, saying, okay, instead of like, give me everything you got, let me take a look at it and see what I need to do, and then I'll give it back to you. Keep it for me, right? That's kind of silly. Okay. So, Volt, why? Why do we actually? Why am I talking about this? And why is it relevant to you, right? So one of the things is that we know microservices architecture. We've been deployed in such architectures. We've actually been seen as slight deviations from the norm, so to speak, just because of the fact that that is what gives you the edge, right? So the architectural considerations that you need to go through when you're designing your microservices stack architecture, how can VoltDB fit in there? And do you even need VoltDB, right? So those are things that we can actually do considerations on. We've been actually working with telcos since 2011, 2012. So we've been steeped in the highest rigors of fast data processing, right? So, and now for people who know about 5G, microservices is pretty much a mandate, right? So if Volt doesn't work in microservices, we're pretty much on our bum on the street. So, so that's our experience. You can tap into, right? So we combined everything that needs to happen in real time for most efficient and effective use of your fast data. We bring all of those things together, right? So, and when you look at the efficiency of VoltDB, we just don't distribute data at the node level. We actually distribute it at CPU core level. So very, very, very high levels of parallelism compared to a sharded environment, for instance. Take like I don't know, like MySQL or MongoDB or whatever be it, and then you say sharding, like you're still looking at independent nodes being monolithic architecture of their own, but they're parallelized at the node level. We go further beyond and create a parallelization at the CPU core level. So, the audience is technical, so I don't think like I'm going deep enough here. So hopefully we're okay with that. Then, the list that I've put together here is just a few examples of where Volt has been used for mission critical real-time applications, right? So in a microservices environment. So if any of these resonate to you, or you go check out VoltDB, like I think that's the next one. Yeah, okay. So how can we help you as your organization representative? One of the things is you don't need to ever talk to us. Just go to voltdb.com, download VoltDB, play with it. But since we are a different kind of an architecture, we would encourage you to talk with us so we can discuss your use case. On the other hand, if you actually have done your research already, we have a program called Enterprise Lab Program, which is a no-cost initiative where you get a license for free use in non-production areas, right? So now, if you don't even know like if VoltDB is right for you or not, I would highly recommend going to our resources section, checking out our white papers and case studies to say like, okay, is there something that we have done that is similar to you? And if you cannot find, do feel free to talk to us. And we're not the kind of people, because we are designed for a specific purpose, we're not the kind that's going to come and say like, you want that? Yeah, of course we can do that. No, that's not our approach. We check applicability of VoltDB, and if there is none, we advise and recommend alternate approaches, and stay friends after that. So that's my session today. Hope you found it useful. So let's move on to question and answers.
Great, thanks, Raj. Yeah, we're going to open the webinar to any questions. So if you have anything you'd like to ask, you can submit them now through the questions tab. So first question, can VoltDB work with Kubernetes?
Yes, actually, in fact, in the telco world, that is becoming like a mandate for us. So we've actually done a lot of work on Kubernetes integration and lifecycle management of VoltDB through Kubernetes for managed and guaranteed availability. Okay.
Great. And can VoltDB integrate with distributed log systems like Kafka, Kinesis, and PubSub in a command orchestration model?
That's an interesting question, right? So one of the things that when I talk about like bringing state and stream together is being able to integrate with your existing systems. Like if you look at the major distributed log systems, like most of them are cloud, other than Kafka, Confluent, Kafka. So we integrate with all of these because we recognize that these are probably already in your system. So what we have done is, because we're specialized technology, we essentially have a front-end integration and a back-end integration into streaming technologies like Kafka or Kinesis. So on the importer side, we can take the data directly from the stream and push it into Volt work function, store procedure, whatever you want to call it, right? Like so, and on the back end, we can actually push out notifications through our exporter framework. So it fits very well with the command orchestrator model, but also you want to be, to my earlier point, you want to be mindful of how do you manage resiliency on the orchestrator. On the other hand, is there a way that you can actually move that work into Volt to say like, here is a message, and Volt, you know that it is coming from this channel, this topic, whatever be it, you know what to do, and all the exception handling is within this stream processing function within Volt, and then you can actually emit signals based on what your end criteria is or end state is of that business transaction, right? So we integrate with all of those, and that's the model, importer and exporter, and between is your transactional processing and decision making. Okay.
And is VoltDB available as a PaaS offering with AWS RDS?
It's not. It's not. We're not on the RDS, but we are on AWS Marketplace, and you can perhaps like work with us to see like how we can actually make it like serverless through the Kubernetes integration. So that's one way to approach it. We run on AWS a lot, mostly in VM models, but more recently in containerized models. So something that we can actually look into it. But we're not, as a past, offering on AWS today.
Great. Now, what about network enhancements like network service mesh? Will that help with data movement?
Well, I mean, if one is actually hell-bent on, I want to have it in a NoSQL store because somehow, like, it actually, accelerates my development cycle. So I'm going to keep it as NoSQL, but I'm looking for network enhancements. Of course, you can do it, but you will actually hit limits. And the limits would be artificial because of the choices, right? So make a different choice and you'll see different limits. So yes, I think there is a commercial organization, Istio, if I'm not mistaken, that has a commercial version of network service mesh, but also it's actually becoming an open source initiative of its own. So I haven't done any personal work there, but it should help. If that's your architectural choice, it will help. Think differently. That's all I can tell, right? Like so.
Great. I believe we have time for just a couple more questions. How different is running VaultDB on a container than running it on a VM? And do you see any advantages for either approach?
Yes, right. So first of all, VMs have slightly better interfaces than containers from networking standpoint, but containers, you can actually declare your entire application as a pod and just spin the whole thing up like within a few seconds, right? So it's massive difference in agility standpoint. From beefiness standpoint, probably VMs are slightly better, but VMs do carry the cost of the hypervisor, right? So while containers don't, they just run directly on the kernel. So I would say definitely containers are advantages. One thing that containers would actually have challenge with, I guess, if you can address it, is the durability part, right? So we're an in-memory database. One of the things that you do is actually run data in memory. So, but you don't want to lose the data. So we offer you 100% durability. In containerized world, that's actually a bit more difficult because you're actually going to some kind of a NAS for network access storage for your durability contracts. That defines like what kind of a pipeline you have with your NAS, right? So on the other hand, VM could have native storage, localized local machine storage, and things like that. So that's another consideration that you can actually think of. Okay.
Great. I believe that's all the time we have for today. Before we go, I just want to quickly throw it back over to you, Dheeraj, for one final thought or one key takeaway you want to leave the attendees with today.
Absolutely. So just because I'm from VaultDB, I'm not going to say like, every microservice implementation needs VaultDB. It depends on your application. So, but if your application requires low latency, high complexity decisions at scale, and perhaps scaling into the future, VaultDB is definitely a great choice for that, just because of the fact that we know from our personal experience the shortcomings of going by the default implementation and what are the nuanced modifications you need to do to your architecture to tap into this capability of VaultDB, right? So I would highly encourage you to talk to us. Hope to hear from you soon.
Thanks, Dheeraj. I just want to remind the attendees that this webinar will be recorded and available by tomorrow if anyone missed anything or would like to go back over, and the slides will also be available. Again, that was Dheeraj Rammella, Chief Technologist at VaultDB, and I'd like to thank VaultDB for sponsoring today's event, as well as the attendees for joining us today. Until next time, I'm Christina Cardoza with SD Times.
Thank you so much for coordinating this, Christina, and thank you everyone for attending this session.